Welcome back to the deep dive. Today we are jumping into, well, what looks like a genuine breakthrough in large language models.
It really does. We're talking about the launch of Falcon H1 Arabic.
And this isn't just another small update, is it? It feels like a major structural shift for Arabic NLP.
It is, and that shift was driven by, very specific community feedback. The older models were good, but people needed more.
What were the main pain points?
Three big ones. They needed dramatically better long context reasoning, much better handling of all the different Arabic dialects, and just, frankly, stronger math performance.
I see. So Falcon H1 Arabic is the engineering answer to all of that.
Precisely.
Okay, so let's get into the blueprint then. Our mission for this deep dive is to really unpack the two biggest innovations here.
The new hybrid architecture and the absolutely massive context windows.
Let's start with the architecture, the Falcon H1 hybrid. What exactly does that mean?
It's a really exciting fusion. They've integrated the efficiency of state space models, which you might know as MAMA, with the traditional analytical power of the transformer attention mechanism.
So how does that work in practice? Is one just bolted onto the other?
No, and that's the key. They run in parallel, inside every single block of the model.
In parallel?
Yes. The Mamba and the transformer attention compute their representations at the same time, and then they're fused together.
And why is that so important?
Because you get the best of both worlds. Mamba gives you this incredible linear time scalability, so the system doesn't get bogged down as the text gets longer.
It stays efficient.
Right. But you also keep the transformer's ability for that really precise, high-fidelity modeling of complex connections across a huge document.
And this hybrid design is in all the new models?
All of them. The 3B, the 7B, and the big one, the 34B parameter model.
Wow. Okay, let's talk about that second innovation, the context capability.
It's a huge leap.
The old limit was what, 32K tokens?
Yes. And now the 3B model is at 128K. And both the 7B and 34B models stretch all the way to 256K tokens.
256,000. It's hard to even picture that. What does that translate to in, say, words?
It's roughly 200,000 words. Think about that. You can process several novels or hundreds of pages of technical documents in a single pass.
Like legal or medical records.
Exactly. And they trained it specifically to avoid that lost in the middle problem, so it can actually find information from the very beginning of that huge window.
But with that much context, the training data has to be, well, perfect.
Or as close as you can get. They moved away from just using basic filters and implemented deep linguistic analysis for the data pipeline.
So really understanding the language, not just keywords.
Right. And they focused on dialect coverage. Because Arabic isn't just one language. They trained on Egyptian, Levantine, Gulf, and Maghrebi Vale dialects, plus the formal modern standard Arabic.
What about other languages, for things like coding?
Good question. They kept a multilingual mix, Arabic, English, and other content totaling 300 billion tokens to make sure STEM and code reasoning were still top-notch.
And the performance results seem to prove it all works.
They really do. Falcon H1 Arabic is state-of-the-art at every scale on the Open Arabic LLM leaderboard.
And I saw that the 34B hybrid model is actually outperforming much larger traditional models, like ones at the 70B scale.
That's the efficiency of the hybrid architecture paying off.
So how should you think about using the different sizes?
The 3B is all about speed. Think edge devices, fast agents. The 7B is your all-around workhorse for enterprise chat or summarization.
And the 34B?
That's for the really high-stakes tasks, complex legal analysis, deep academic research, where you need that incredible long-range reasoning.
Of course, with high-stakes tasks, we have to mention responsible AI. There still need to be guardrails, right?
Oh, absolutely. These models can still reflect biases from their training data or, produce hallucinations, especially when you push that massive context window to its absolute limit.
So human verification is still a must.
Mandatory, especially when the stakes are high.
So to wrap up this deep dive, the two key takeaways are a fundamentally new parallel hybrid architecture.
The Mamba transformer fusion.
And an absolutely unprecedented 256K token context length, which completely redefines scale for Arabic NLP.
Right. And if you connect this to the bigger picture, it leaves you with a really provocative thought.
Go on.
The fact that a 34B hybrid model can outperform a 70B traditional transformer, well, it forces you to ask a question. What does this mean for the future of LLMs globally?
You mean beyond just Arabic NLP?
Exactly. Are we moving to a world where efficiency, this smart architectural design, becomes more important than just adding more and more parameters?
Yeah.
That's something for you to mull over.
Welcome to the deep dive. Today, our mission is a really interesting one. We're looking at K-EXAONE, the large-scale model from LG AI Research.
Hmm.
And what's compelling here is that this isn't just about a new model. It's really a story about strategy, about how South Korea is trying to compete in this, intense global LLM race.
Right, despite facing some major infrastructure challenges.
Exactly. The GPU shortages, the lack of specialized data centers, all of that.
And that's the thing, when you can't just, outspend everyone on hardware, you have to be smarter. You have to out-engineer them.
So the government stepped in.
They did, yeah. They launched a strategic program to secure resources, like GPUs, but the model itself, at its core, had to be incredibly efficient just to bridge that gap. K-EXAONE is really a great example of innovation that's born from scarcity.
Okay, so let's unpack that efficiency. It starts with the architecture, right? A mixture of experts or MOE design.
That's right. The model is huge. I mean, 236 billion total parameters.
Yeah.
But, and this is the key, only a small fraction of that, about 23 billion, is actually active during inference. So you get the power of a giant model without the massive computational cost every single time.
I see. And they also focused on speed, not just size.
Exactly. They added something called the Multi-Token Prediction Module, or MTP. If MOE is about capacity, you can think of MTP as being about quickness.
So what does that actually do?
It's sort of a self-drafting mechanism.
Yeah.
Lets the model predict several steps ahead instead of just one token at a time. And that boosts the decoding speed by about 1.5 times when you're using it.
Okay, so that's the efficiency piece. But the other side of this is sheer scale. It's memory, right? A 256K token context window, that's pushing the industry maximum.
It's an incredible number. And getting there wasn't simple. It took a two-stage process, essentially training the model to handle larger and larger documents, first from 8K up to 32K.
And then the big jump.
And then the big jump all the way to 256K.
But wait, doesn't stretching a model's memory that far cause it to sort of forget how to handle simple, short questions?
That is a critical concern, and they thought about it directly. To prevent that kind of performance drop on short context tasks, they used what they called a rehearsal data set.
Like flashcards.
Pretty much. Think of it like a core curriculum. While it's learning to handle these huge documents, the model is constantly rehearsing high-quality short samples to keep its fundamental skills sharp.
So with all that power and efficiency, how does it actually perform?
It's very competitive. In its reasoning mode, it hits a score of 83.8 on MMLU Pro and a really striking 92.8 on the AIM 2025 math benchmark.
So it's often leading other open weight models there.
It is. And its multilingual capability is really strong, too. It covers 6 languages. Korean, of course, but also English, Spanish, German, Japanese, and Vietnamese.
And it's balanced across them.
Very balanced, yeah. It scored an average of 90.5 on the WMT24 plus translation benchmark, which suggests a deep, genuine multilingual ability.
This brings us to what I think is the real aha moment here, the thing that truly sets K-EXAONE apart, its approach to safety.
All right. Everyone's focused on universal ethics, but LG AI Research built an in-house benchmark called KGC Safety.
And this is built on a specific framework.
It is. It's called the Korea Augmented Universal Taxonomy, or KAUT. And this is where the regional strategy becomes so clear. It doesn't just use standard ethical principles. It actually merges them with specific Korean cultural and geopolitical sensitivities.
That sounds incredibly complex. Can you give us a concrete example of what a risk under that kind of augmentation looks like?
A perfect one is under their Korean sensitivity domain. K-EXAONE addresses specific localized risks, like discrimination against North Korean defectors.
Oh, wow.
And things like historical distortions. These aren't just vague ideas. They require the model to adhere to domestic laws and verified historical facts. And it works. K-EXAONE gets a safe rate of 96.1% on this benchmark.
So what does this all mean for you? K-EXAONE is really defined by 3 pillars. That super efficient MOE scaling, the huge 256K long context capability, and, critically, this culturally augmented safety.
And if you want to use it, the model is available under both commercial and non-commercial licenses. But you do have to agree to some strict ethical rules. No fraud, no harmful content. And importantly, LG AI Research claims no ownership over anything you generate.
So here's the final thought. The integration of this kind of cultural specificity into AI safety through a framework like KAUT, it really changes how we have to think about responsible AI. If every major language model needed to incorporate these kinds of deeply nuanced regional and historical sensitivities to be considered safe, what would the next truly universal ethical AI framework even look like? Something for you to chew on as you continue your deep dive.
Welcome to the Deep Dive. Today we're doing a crash course in high-fidelity video phase swapping, or VFS. And if you've ever really looked closely at a deepfake, you know the biggest issue. It's that moment the person turns their head or, makes a big expression.
And the whole thing just falls apart.
Exactly. The face flickers, the identity breaks, the consistency frame to frame is just not there.
Okay, let's unpack this. We've been looking at this new research from Tsinghua University and ByteDance, and they've built a framework called DreamID-V.
Right.
And their goal is, well, it's pretty ambitious. They want to take the amazing quality you see in still image face swapping IFS and just lift it directly into video.
And solve that flickering problem for good.
That's the idea.
But that jump from a static image to, a dynamic video seems to be where everything breaks down. An IFS model can give you one perfect frame, but when you stitch them together...
You get jitter, you get artifacts, there's no temporal consistency. Exactly. So they realized they couldn't just generate perfect video data out of thin air to train on.
But what did they do?
They created something really brilliant called the SyncID pipe. It's a data pipeline. And the core idea is, instead of trying to create new video data, they use the best existing image models to generate these bidirectional ID'd quadruplets.
So they're using the gold standard from images to teach the video model.
Precisely. They're training the video model on what a perfect still frame should look like. And to handle the motion, they have the identity-anchored video synthesizer, the IVS.
Okay, and that part handles the movement.
It's like a motion director. It uses what they call an adaptive pose attention mechanism, which basically locks in the motion from the first to the last frame, making sure the face moves coherently within the scene.
Here's where it gets really interesting for me, the architecture. I read that DreamID-V is the first VFS framework built on a diffusion transformer, a DIT model.
Yeah, that's a major step up.
So how does an architecture like that juggle all these different inputs? You have the identity, the background lighting, and all this complex motion data coming from the IVS.
It uses a very clever system called modality-aware conditioning, or MC. You can almost picture the DIT as an intelligent switchboard.
Okay.
The MC makes sure that 3 different kinds of information, the context like lighting, the structural guidance for pose, and the core identity, are all injected separately. It disentangles them so the signals don't get mixed up.
That makes sense.
Yeah.
But starting with synthetic data, doesn't that risk making the final video look a bit fake, a little sterile or detached from reality?
It would, which is why they have a 2-stage training strategy. They start with synthetic data to get the identity similarity down fast, just teaching the model who it's supposed to be.
And the second stage?
That's the real augmentation training. They fine-tune it with real paired data and use this enhanced background recomposition to make sure it looks realistic and preserves the original background. It irons out all that artificial stiffness.
But there's one more piece, right? The thing that actually stops the flickering.
Yes, the secret sauce. It's a strategy called Identity Coherence Reinforcement Learning, IRL.
So wait, this is like a tutoring system for the AI. It actively rewards the model for getting the hard parts right.
That's a great way to put it. The IRL system identifies what it calls difficult frames. A quick head turn, a profile view, a big laugh. The exact moments where identity usually fails.
And it focuses the training there.
It gives those frames a massively higher learning weight. It basically penalizes the model much more for failing on the hard stuff, forcing it to get better at temporal consistency across the whole video.
And the results seem to speak for themselves. DreamID didn't just get better video quality. It actually surpassed some of the previous image models on identity similarity.
That's kind of wild for video.
It really is. And they released a whole new benchmark, ID-Bench-V, to go with it, basically setting a new standard.
So what does this all mean? It sounds like DreamID-V proves you really can transfer the power of these incredible image models into video as long as you can solve the temporal challenges. Exactly. And the framework itself is incredibly versatile. They've shown that you can just swap out the underlying image model and adapt it to other things.
Like what?
Like swapping outfits, accessories, even hairstyles, all in a moving video.
Wow.
So here's a final thought for you to chew on. Considering this diffusion transformer can handle structure and motion so well, what's the most complex non-face attribute it could swap? Think beyond just clothes or hair. Could it, for example, accurately transfer something really fine-grained, like the specific way a certain fabric winkles when someone moves? Or maybe even the texture of aging skin across a full range of expressions? Something to think about. So today we're diving into something that feels like a real architectural battleground in generative AI.
It really is. We're looking at a paper from ByteDance on a model they call NextFlow.
And it feels like they're taking a sledgehammer to the established rules.
That's a good way to put it. For years, the consensus has been, you have LLMs for reasoning, and you have diffusion models for great images. Two separate things.
Right.
NextFlow says, why not one? It's a purely autoregressive system, a 7 billion parameter decoder-only transformer that tries to do it all in one go.
Okay, let's unpack this. One single model for interleaved text and images. But wait a minute. Autoregressive models for images. Haven't they always been incredibly slow, like prohibitively slow?
That is the core problem they had to crack. And you're right. The standard raster scan method, it's just painstaking. It builds the image sequentially.
So you're talking, what, 10 minutes or more for a single high-res image?
Easily, yeah. Over 10 minutes for a 1024 by 924 picture. It's just not practical for any real-world use.
So that's where the breakthrough had to happen. And it did. They call it next scale prediction.
Mm-hmm. It's a completely different paradigm.
And the numbers are just, they're staggering. They took that 10-minute task and knocked it down to 5 seconds.
5 seconds. And with 6 times fewer computations, fewer FLOPs than the top-tier diffusion models.
That's the efficiency that suddenly makes this whole unified idea, well, viable.
But that speed means nothing if the image quality falls apart, which is a classic failure mode when you try to scale these AR models up.
Right, you get weird artifacts, structural problems.
Exactly. So their solution, and this is the clever part, was scale-aware loss reweighting during training.
Okay, what does that mean in simple terms?
It means they essentially told the model, get the big picture right first. They heavily prioritize the coarse early tokens, the ones that define the overall layout.
Like a blueprint.
Precisely.
Mm-hmm.
Build the blueprint first, make sure the structure is solid, and then worry about coloring in the fine details.
And that stable foundation is what unlocks everything else, right? More advanced stuff like editing and reasoning.
It's the key, because now you have a fast, stable, unified system. So when it comes to complex image editing, it excels.
I saw the numbers on the Edit Canvas benchmark.
An overall score of 8.04, state-of-the-art. But the really striking result for me was identity preservation.
Mm-hmm. The Omni context test?
Yeah, it scored a 9.22 on keeping a subject consistent through edits. That's better than Jeep 340 on that specific task. That's a huge deal.
And because it's all one sequential process, it can do what they call thinking with images.
Which sounds like marketing, but it's actually a perfect description.
It's chain of thought reasoning, but it happens before the image is even generated.
Right. The model can literally think to itself, okay, the request is for China's national treasure. That's a giant panda, not a red panda. It self-corrects.
And that actually improved his performance.
Substantially. Adding that chain of thought step boosted its logical consistency, the WISE score, from 0.6 all the way to 0.70. It proves the architecture helps it think better.
So when you put it all together, what are we looking at here? NextFlow seems like a radical proof of concept.
It is. It shows that a single decoder-only transformer can perceive, reason, and create across modalities.
Mm-hmm.
It challenges that whole idea that you need separate hybrid systems.
The future might just be unified, full stop.
And if you zoom out to the bigger picture, this unified AR structure has a unique advantage.
Mm-hmm.
You can apply standard reinforcement learning techniques directly to its reasoning paths.
Something a hybrid model just can't do as cleanly.
Not at all. They call it native multimodal chain of thought and unified RL. It's a pathway to self-improvement that's built right into the architecture.
And they're already talking about what's next, swapping out the dense architecture for a mixture of experts or MOE framework.
Which would scale it up massively.
So here's something to chew on. If a model like this keeps scaling with MOE, how does that change our very definition of visual and textual coherence when it all comes from one single dynamic mind?